something changed. In the early hours of November 7th, telescopes in both hemispheres captured a shift. 3I Atlas, the interstellar object that's defied every model of comet behaviour, was no longer whole. What was once a single, compact object now appeared split. Two cores, one marginally dimmer than the other. No explosion, no debris field, just a clean bifurcation. But only one half stayed visible. The other? It vanished, directionally, deliberately, as if peeling away on a path of its own. For months, astronomers struggled to understand its unnatural acceleration, its refusal to vent gas, its precise behaviour. Now we have a new mystery: fragmentation without a cause, and a missing fragment. Tonight, we'll trace the data. From light curve irregularities to spectral anomalies and orbital bifurcation models, we'll ask the question most scientists are still whispering. If 3I Atlas just split in two, where did the other half go? Like, subscribe and drop a comment with your time zone and thoughts. You're part of a community tracking this in real time, and this story just took a darker turn. On the morning of November 7th, 2025, something unexpected occurred in deep space. Something subtle, silent, but profound. Astronomers tracking the interstellar object known as 3I Atlas noticed a faint elongation in its structure. At first glance, it looked like a common artifact of long exposure imaging, the kind of blur you get when a fast-moving object is tracked imperfectly across a telescope's field of view. But then it persisted. Across multiple observatories, at different latitudes and using different instruments, the same distortion appeared. Not fuzzy, not chaotic, but structured. 2 points of light close together, moving in tandem. It didn't take long for the confirmation to settle. 3I Atlas had split in two. This event marked a dramatic turning point in the mystery of 3I Atlas, an object already defying conventional models of cometary behaviour. Unlike previous fragmentations observed in solar system comets, which tend to be violent, explosive, and leave visible trails of debris, this was eerily clean. There was no observable coma expansion, no dust plume, no sudden brightening or drop in magnitude. It was, for all intents and purposes, a quiet separation. The fragmentation of comets typically involves thermal stress, rotational instability, or internal gas pressure. As a comet nears the Sun, it heats up, causing ice within to sublimate and expand. This pressure can rip weaker comets apart, creating chaotic jets of gas and dust and sometimes dozens of irregular fragments. But 3I Atlas had shown none of the thermal behaviour consistent with such stress. In fact, in the days leading up to the split, its light curve remained flat, a magnitude between 14.7 and 14.9, stable and uneventful. So what exactly caused the split? The answer is still unclear. What we do know is that the separation appeared directional. The two objects, let's call them Object A and Object B, remained close at first, moving side by side as if one had gently peeled away from the other. Over the course of the next 6 hours, Object B began to diverge, moving at a slight angle from the original trajectory. The angle of separation was small but measurable. This wasn't a random break, it resembled a release. In a normal cometary split, fragments tumble, their spin increases, material begins to outgas unevenly, but here the fragments stayed smooth, composed, and silent. Observatories attempting to capture a coma, the fuzzy cloud of gas and dust typically surrounding an active core, reported nothing. No jets, no flares, just a faint second core, dimmer than the first, moving away with intent. This raised deeper concerns, because if the second object wasn't a fragment, what was it? Initial orbital analysis indicated that Object A, the brighter of the two, remained on its previously calculated hyperbolic path. But Object B's slight deviation hinted at acceleration. The separation wasn't passive, it had force behind it. And yet, there was no visible thrust, no flash of light, no ejected mass that could explain such propulsion. Which means we were likely witnessing a non-gravitational event, a change in motion that couldn't be accounted for by natural forces alone. In isolation, a splitting comet is rare but not alarming, but in the case of 3I Atlas, an object already suspected of behaving more like a vehicle than a natural comet. This changes the stakes, because now the question isn't just, what is 3I Atlas? Now the question is, what did it just deploy? One fragment remains visible, the other has begun a new journey. And we were lucky, or perhaps unlucky, to witness the moment it all began. When space fractures, we expect noise, not literal sound, of course, because in the vacuum of space there's none, but we expect visual chaos. We expect jets, clouds, ejected trails of ice and dust, expanding like smoke in sunlight, especially when a comet, or what we believe to be a comet, breaks apart. But 3I Atlas didn't follow the script. On November 7th, 2025, after weeks of suspiciously precise behaviour, the interstellar object designated 3I Atlas quietly split in two. There was no burst of brightness, no expansion of a coma, no flaring in spectral emissions, just a subtle shift, 2 points of light instead of one, and the realization that something important had just happened. In standard comet science, fragmentation is a messy event. Heat from the sun penetrates a volatile-rich nucleus, causing rapid sublimation of ices. The trapped gases expand beneath the surface until pressure builds to the point of rupture. What follows is almost always violent. The object fractures unevenly, throwing material into space, creating expanding dust clouds, multiple visible fragments, and highly variable light curves. That didn't happen here. Observatories across multiple continents captured the moment 3I Atlas broke apart. The split was too clean, the brightness of the object didn't spike, its surrounding space remained remarkably empty. No signs of ejector, no visible coma broadening, and no emerging debris trail. If you weren't looking closely, and didn't know exactly where to look, you'd miss it entirely. This was not just a break, it was a silent break. Even stranger, both resulting cause, the original and the faint secondary object, remained coherent. They didn't spin erratically, they didn't tumble out of control. Instead, they drifted apart slowly, maintaining a consistent geometry. In fact, their relative motion in the first few hours suggested a controlled separation, not a chaotic rupture. For the scientific community, this presented a paradox. If the split was caused by internal pressure, why didn't we observe the explosive symptoms? If it was due to rotational instability, why wasn't there measurable spin variation in the light curve? If it was a structural failure, why did both components stay intact and remain visually stable for hours? One possible answer emerged. This wasn't a natural break at all. The timing itself deepens the mystery. The break occurred just days after 3I Atlas's perihelion passage, when it should have experienced the most thermal stress. But thermal modelling of the object, based on its lack of outgassing and dust, suggested its surface wasn't behaving like an ice-rich body. There was no visible heating effect, no jet activity, and now no expected rupture symptoms. So what could cause an object in deep space to split, without heat, without jets, and without visible force? That question has no clear answer, but one hypothesis is gaining traction. The split may have been intentional. In this model, 3I Atlas is not a comet, but a composite structure, an interstellar system made up of multiple internal components. These components remained fused during its journey through interstellar space, only to separate once solar proximity was achieved. The secondary object could be a data pod, a probe, or even a reaction mass used for thrust. If true, this wouldn't be a comet falling apart. It would be a system activating, and it would explain the silence. Engineered systems do not erupt. They separate on command. They release, deploy, pivot. They leave no jets because they don't rely on gas pressure. They leave no coma because there's no ice to sublimate. They do only what they're meant to do, with precision, symmetry, and intention. And that's what we saw. A perfect quiet split. No dust, no panic, no flare, just a deliberate event in the dark, and a mystery deepening by the hour. After the mysterious split of 3I Atlas on November 7th, 2025, global attention turned to the brighter of the two fragments, the object that remained on the original trajectory. For the purposes of clarity, astronomers designated it Core A. It was the dominant signal, the body previously recognized as 3I Atlas before the bifurcation event, and in the hours and days that followed, Core A behaved like nothing had happened. Photometric data remained consistent. Its visual magnitude, which had been oscillating gently between 14.7 and 14.9 in the weeks prior, showed no sudden jump or dip. There was no spin instability, no visible mass loss, no indication of stress. To anyone unaware of the separation, Core A looked identical to its pre-fragmentation self, a cold, consistent interstellar traveller gliding along its hyperbolic course. That was the first red flag. In natural fragmentation events, the primary body typically shows some response, even if it's just a wobble in its light curve. Structural shifts can cause rotational precession. Loss of mass can nudge the object off course. If gas or dust is released, a coma may form or expand. Yet here, none of those standard indicators appeared, so astronomers began to dig deeper. High-resolution imagery from the Virtual Telescope project and the Unnaves Observatory showed that Core A had retained its point source geometry. No diffusion, no haze, no growing envelope of ejecta. Just a sharp dot, steady, star-like, and composed. That alone separated it from nearly every known comet fragment in recorded history. Then came the spectral analysis. Infrared and ultraviolet scans continued to show a lack of expected molecular lines. No significant water vapour, no carbon dioxide, no cyanogen, nothing that would suggest an icy body venting under solar stress. The only standout feature remained a faint but persistent spike in the green C2 emission band, possibly indicating diatomic carbon, but even that signal had plateaued prior to the split. In short, Core A wasn't behaving like an active nucleus at all. It was behaving like an inert metallic body, and yet it remained bright. This presented a strange contradiction. If the object was truly inert, metallic, dense, and non-venting, then its reflectivity should be relatively low, especially at distance. But brightness estimates from multiple observatories indicated a consistent albedo that implied either an unusually high surface reflectivity or active energy reflection. That's when some researchers began considering alternatives. One model suggested that Core A might not be reflecting sunlight uniformly, but redirecting it, possibly using flat geometric surfaces like panels or sails. This would explain the unnatural sharpness of its light signature and the lack of surrounding haze. It also supported earlier hypotheses that the object's trajectory was being fine-tuned using subtle, non-gravitational thrusts. Indeed, when comparing data from before and after the split, orbital modelling showed a negligible deviation in Core A's path. No course correction, no acceleration spikes, no measurable fallout. It was as if the object had released mass and immediately compensated for it. That, too, is not something a natural object does easily. Some physicists proposed a radical but increasingly considered possibility: mass conservation through internal reaction. That is, if the split was planned and not the result of stress, Core A may have released a secondary component, Core B, while simultaneously adjusting its own momentum, preserving its outbound course. The mechanics of such a maneuver would require internal energy control, possibly some form of contained propulsion, a system capable of keeping the remaining structure balanced and on target. For the moment, however, Core A continues to move forward, unchanged in brightness, unshaken in direction, uncomplicated by the mystery it left behind. But what it didn't do may be more important than what it did. It didn't react. It didn't slow down. It didn't vent. It didn't wobble. It just kept going, as if shedding a component was part of the plan all along. And if that's true, then Core A might not be a comet at all. It might be the front half of something bigger. The moment 3I Atlas split on November 7th, 2025, two separate entities emerged from what had, until then, appeared to be a singular silent body. The brighter of the two fragments, Core A, continued on its projected trajectory, stable and steady. But the second fragment, Object B, took a different path, one that would soon raise more questions than answers. From the very beginning, Object B was fainter. Initial readings placed it nearly 2 full magnitudes dimmer than Core A, still detectable, but at the very edge of what smaller observatories could resolve. Yet for a few hours it was visible, moving just slightly off course, a faint twin drifting apart as if intentionally, and then it vanished. Within 6 hours of its detection, Object B dimmed beyond magnitude 18. Within 10 hours, it was below 20. And by the time a full day had passed, it had disappeared entirely from the optical spectrum. Multiple observatories, using telescopes tuned to both visible and near-infrared wavelengths, attempted reacquisition and failed. The object was no longer reflecting sunlight in any measurable way. To Earth-based instruments, it had become invisible. But how does a solid body vanish in space? To answer that question, we need to break down the possibilities. First, the obvious, disintegration. Perhaps Object B was simply a fragile fragment, torn from the main body during separation, and it crumbled under its own rotational stress. If it broke into micron-sized dust, it might disperse too widely and too faintly to be seen. But that doesn't align with the data. Disintegration typically leaves a dust trail, or at minimum a broadened coma. In this case, no residual haze was detected, no reflectivity increase, no scattering, just a light that faded, cleanly and rapidly. That leads to the second possibility, rotation-induced dimming. If Object B were a tumbling fragment with a low albedo surface, say dark rock or carbon composite, then rapid rotation could cause sunlight to be reflected away from Earth-based detectors. Essentially, it could blink out not because it ceased to exist, but because it turned away. However, models suggest the decline in brightness was too steep and too continuous to be explained by spin alone. A third hypothesis, far more speculative, is that Object B employed active concealment. This may sound extreme, but in the context of 3I Atlas, already exhibiting unexplainable propulsion, spectral silence, and high-precision behavior, it cannot be dismissed outright. Some researchers suggest that Object B may not be a mere fragment at all, but a deployed subcomponent. If it altered its trajectory with a deliberate burst of acceleration, even something as subtle as a low-thrust ejection, and then shifted its orientation, it could reduce its visible cross-section dramatically. More compelling is the fact that some infrared sensors picked up a brief heat anomaly near the time of disappearance. Not heat from sublimation or gas jets, but a localized IR bloom consistent with a fast controlled maneuver. This would imply that Object B wasn't passively tumbling, but steering. Then there's the vector. While Core A continued along its predicted hyperbolic arc, Object B deviated slightly, enough to suggest non-gravitational acceleration. Not much, just a subtle push. But direction matters. It moved away from the solar plane, veering upward on what some have called a shadow vector, a trajectory that leads it closer to the Sun, but also away from Earth's observational line of sight. If this vector holds, Object B could already be well into the inner solar system, taking a route that leaves Earth behind. Its brightness drop could simply be a function of angle. We may no longer be in the path of its reflected light. And if Object B is engineered, then perhaps that was the point. In the end, what's most unsettling isn't that Object B disappeared, it's that it did so without consequence. No debris, no tail, no chaos, just a faint signal that slipped away, intentionally, precisely, and perhaps permanently. Something left us, and we may never know where it went. Fragmentation is not unusual in the life of a comet. In fact, it's expected. As these icy bodies pass close to a star, they endure immense thermal stress. Their cores crack. Pressure from sublimating gases erupts through vents, and eventually the structural integrity gives way, explosively, messily, and usually predictably. But 3I Atlas didn't behave like a typical comet, and its fragmentation didn't follow any known rules. This wasn't thermal stress. This wasn't chaotic shattering. This wasn't natural, at least not in the way we understand nature. From the very first moment the split was detected, on November 7th, 2025, astronomers knew something was different. Fragmentations don't happen in silence. They're typically accompanied by sudden increases in brightness as fresh ice is exposed and begins to vaporize. They often leave behind a cloud of debris, dust, gas, and microparticles that drift behind the comet, forming a short-lived coma or tail. But when 3I Atlas split, there was no brightening, no explosion, no flash. The two bodies simply appeared, separated cleanly, with no evidence of debris or dynamic instability. That's not just rare, it's practically unheard of. Let's look at what typical fragmentation events involve. In comets like 332P Ikea Murakami or C1999 S4 Linear, fragmentation follows a visible escalating pattern. The light curve shows a sudden spike as internal volatiles are released. New fragments scatter in irregular directions, some spiral, others tumble chaotically. The result is visual chaos, a flurry of material, uneven brightness, and unpredictable paths. These are classic symptoms of a rotational breakup or internal overpressure rupture. But 3i Atlas split with symmetry. High-resolution observations from the Virtual Telescope project showed the two fragments, Core A and Object B, aligned along the orbital axis. Not scattered, not misaligned. They stayed in formation for hours, even as their distance slowly increased. That's not fragmentation, that's separation. In fact, the clean geometry of the event suggested a pre-calculated vector, as if Object B was released at a planned speed and angle to diverge gently from the parent body. There was no tumbling, no secondary wobble, no rotational instability. Both bodies remained balanced, even as they drifted apart. This led to an uncomfortable but increasingly discussed conclusion. This was not a breakup, it was a deployment. Comet nuclei are typically irregular in shape, covered in fractures, and full of asymmetrical outgassing vents. This chaotic structure makes clean splits nearly impossible. But 3i Atlas showed signs of geometric precision. The A3 component of its thrust vector, the one measuring out-of-plane acceleration, remained close to zero even after the split, meaning its motion was still confined almost entirely to the orbital plane. That's not what happens when a chunk of rock randomly flies off due to stress. Instead, the available data implies that the separation may have been controlled. Whether through internal propulsion, magnetic torque, or mechanical release, Object B appears to have left Core A with deliberate stability and without disturbing the overall dynamics of the system. There's another problem: mass distribution. In a natural fragmentation event, the mass ratio between the fragments is almost never 1.1. One piece is larger, the others tend to be smaller, more chaotic, or irregularly shaped. But brightness analysis during the early minutes of the split showed a very close luminosity ratio, indicating the fragments were surprisingly similar in size and reflectivity, almost like modules of the same system. The silence, the geometry, the absence of debris, the symmetry, each by itself could be a fluke. Together they paint a picture that is not consistent with known cometary behavior. So perhaps the most accurate statement isn't that 3i Atlas fragmented unnaturally, but that it may never have been a comet to begin with. Because if this wasn't a structural failure, then it was a function, a feature, not a flaw. When 3i Atlas split on November 7, 2025, two fragments emerged. One continued its course, smooth, silent, and seemingly unaffected. But the second, dimmer object, known as Object B, began to drift. Not randomly, not erratically, but purposefully. And it's in that motion, in the angle of its escape, that a deeper mystery reveals itself. Astronomers call it the directional clue. In natural fragmentation events, pieces break away from a parent body along chaotic vectors. Depending on internal pressure, rotation, surface volatility, and solar radiation, fragments tumble and spread. Their courses are jagged. Their velocity vectors fan out. It's messy, dynamic, and ultimately unpredictable, especially for cometary nuclei which are structurally unstable and poorly cohesive. But Object B didn't act that way. Instead of flying off at a steep angle, or spiraling into a dust cloud, it separated along a clean, shallow vector, just slightly offset from the primary orbital plane. Tracking data showed that it maintained a consistent angle of divergence of about 2.7 degrees, not upward, not downward, but along a precise off-axis trajectory. And this angle matters, because until that moment, 3i Atlas had displayed a non-gravitational thrust profile that baffled physicists. Its motion was tightly confined to the orbital plane, with no measurable deviation in the third dimension, what astronomers refer to as the A3 component. It was as if the object had been deliberately avoiding motion outside of the solar system's flat disk, the ecliptic. That kind of constraint isn't natural. Natural outgassing from comets creates chaotic, multi-directional thrust. A zero A3 value implies discipline, or control. But now, for the first time, Object B broke that pattern. This divergence immediately triggered a round of recalculations. Observatories ran simulations. If this motion were the result of a simple breakup, the fragment should have displayed random tumbling and an unpredictable arc. But it didn't. The escape vector was consistent with a low-force lateral push, enough to slowly peel the object away from core A, but not enough to suggest a violent release. This subtle deviation may seem insignificant on paper, a couple degrees, a few meters per second, but in the vacuum of space such small changes compound rapidly. Within just 24 hours, the two fragments were already thousands of kilometers apart, and Object B was no longer visible. Its path was now beyond optical acquisition, but its direction remained known, and it wasn't just drifting, it was heading toward the Sun. This is critical. Most comet fragments move away from the Sun after perihelion. Solar pressure and outgassing push debris outward, creating tails that extend away from the source of heat. But Object B's trajectory was curving inward, toward greater solar intensity, and potentially, depending on timing, into a zone of gravitational slingshotting. If you were designing a small probe to use the Sun's gravity or radiation pressure for maneuvering, or hiding, this would be the angle you'd choose. Then came the radio silence. As Object B faded from optical view, researchers scanned in other wavelengths: radio, infrared, ultraviolet. In each, the signal was flat. No emission, no thermal signature, no outgassing. But some telescopes detected a brief dip in charged particle density along its projected path, a potential indication of shadowing or shielding, which raised an unsettling possibility. What if Object B didn't vanish because it disintegrated? What if it vanished because it cloaked itself by design? Taken together, the directional clue suggests one of two possibilities: a coincidental geometry, a fragment just happened to break cleanly, at an unlikely angle, with minimal disruption, and disappeared naturally. A controlled maneuver, an engineered release on a precise path, possibly pre-programmed, using internal mechanisms to avoid detection and guide itself deeper into the system. And if it's the second one, then we may have just witnessed a deployment event, not a break. Something launched, and its angle, its directional clue, might be the key to everything that follows. The laws of motion in space are simple, or at least they're supposed to be. For every action, there must be an equal and opposite reaction. If something accelerates, it must push against something else. If a comet changes speed or direction, it must be venting gas, ejecting dust, or shedding mass. But in the case of 3I Atlas, and particularly in the behavior of Object B after the split, that rule seems to have been violated, because Object B moved, and it moved with purpose, without ejecting anything visible at all. Shortly after its separation from Core A on November 7, 2025, Object B began to drift away at a shallow angle, following what astronomers now call a non-gravitational escape vector. Observatories tracked its path closely in the early hours after the split, and what they discovered was striking. The fragment was accelerating. Not drastically, but enough to be measurable. Estimates placed the lateral acceleration at roughly 3 s10⁻⁷ AU day 2, consistent with a small but sustained thrust. That kind of motion cannot occur without energy input, and in space there are only a few known ways to generate that kind of force: gas outgassing, as seen in normal comets; dust ejection, from internal pressure or heating; solar radiation pressure, pushing on high surface area structures; or active propulsion, artificial thrust using internal energy reserves. So which one explains Object B? Let's start with the obvious: outgassing. If this were a typical comet fragment heated by the Sun, you'd expect gases like water vapor, carbon monoxide, or cyanogen to begin sublimating from its surface. That gas would produce a gentle thrust, pushing the object along its new path. But there's a problem. Actually two. First, there was no coma, no tail, no haze, no brightening. Second, there was no spectral evidence of any volatiles being released. Instruments specifically calibrated to detect molecular emission lines came up blank. No spikes in water bands, no ultraviolet flaring, no green C2 emissions, just darkness. So, if the object wasn't outgassing, how was it accelerating? This led researchers to test a more exotic possibility: solar radiation pressure. If Object B had an extremely low mass-to-area ratio, Like a thin reflective surface, the constant push of photons from the sun could gradually alter its path. Think of it as a solar sail. This wouldn't require heat or exhaust, just structure. The math even works. Over hours and days, such pressure could create exactly the slow, consistent motion that was observed. But there's a catch. Solar sails are visible. They reflect light. They glint and flare depending on their orientation. But Object B didn't brighten. It dimmed. Fast. Within hours it faded beyond magnitude 20. Beyond detection even for most deep sky observatories. Which leaves us with the most controversial option. Internal propulsion. What if Object B wasn't a passive fragment at all? What if it contained a compact energy source, chemical, thermal or even nuclear, and used that energy to push itself along a predetermined course? A tiny ion drive, a directed vent, a cold gas thruster. The possibilities exist, in theory, in design, and even in the experimental payloads of Earth's own spacecraft. And in that context, the silence makes sense. There would be no visible jets, no plumes, no tail. The acceleration would be clean, controlled, and silent, like a machine sliding across rails no one can see. What's most important is that energy was spent. The motion of Object B cannot be explained by gravity alone. Something provided the force, and yet nothing was ejected, nothing detectable anyway. That fact changes everything. Because comets do not accelerate in perfect silence, debris does not glide with intent, and fragments do not vanish without a trace unless they were never fragments at all. What we're seeing may not be an accident. It may be the signature of an object acting with purpose, and in the vacuum of space, purpose leaves no fingerprints. Only motion. When something moves through space, especially at high velocity, it leaves behind traces. Not always visible to the naked eye, but detectable. Comets leave wakes. So do spacecraft. So do fragments of asteroids and meteors. They all disturb the space around them, even subtly. But with 3I Atlas, and specifically with Object B, the fainter fragment that separated on November 7, 2025, there was no wake, and that's a problem. From the moment the split occurred, astronomers scrambled to point instruments at the event. Dozens of observatories, both amateur and professional, captured the separation and began tracking both bodies. Core A stayed bright and stable. Object B drifted away at a shallow, deliberate angle. But when researchers analysed the region of space behind Object B, what they found was shocking. Nothing. No dust trail, no gas cloud, no residual coma, no light-scattering debris. The void left in Object B's path was cleaner than expected, and far too clean for any natural fragment moving at interplanetary speeds. Here's why that matters. Typical comet fragments, even those produced by non-violent separations, leave material behind. Outgassing may be minimal, but sublimating ices still push tiny particles into space. Some of that dust lingers. Some trails behind the object in curved lines due to solar radiation pressure and momentum drift. These particles scatter sunlight and can be detected by photometric instruments as faint streaks or glow patterns. Even more subtle, when a body accelerates in a new direction, like Object B did, conservation of momentum implies that some small portion of material must have been pushed away in the opposite direction. That reaction, even in low-energy scenarios, tends to leave detectable disturbances. In Object B's case, however, such signs are conspicuously absent. Let's examine this from a physics standpoint. If Object B used any sort of internal propulsion, it should have expelled mass, even a tiny amount. Ion drives, for instance, use particles like xenon to create thrust. Cold gas thrusters release compressed gases through narrow nozzles. Both leave behind faint trails of ionized or excited particles, even if they're nearly invisible to the human eye. Yet high-sensitivity spectrometers trained on the region, in the hours and days after separation, found no emission lines. No signature of ionized gas, no temperature differential, not even dust haze. So we face a question that shouldn't exist. How did an object accelerate without disturbing the medium it travelled through? There are only a few plausible answers, and none are comfortable. One explanation is stealth design, not in the military sense, but in terms of particle control. If Object B was engineered with a propulsion system designed to emit mass directionally and in microscopic quantities, and if that system aimed away from Earth's line of sight, it could theoretically produce motion without visible wake. That would require precise ejection symmetry and the ability to avoid reflection or dispersion in the optical range. Another explanation is massless propulsion, something like light pressure manipulation or electromagnetic field interaction. These are speculative technologies, but not outside the realm of possibility. A material that could harness solar photons with ultra-low mass could drift along controlled vectors without releasing dust or gas. That would fit the behavior observed, but would place Object B far beyond what we understand of naturally formed bodies. Then there's the most extreme hypothesis: displacement without ejection. A system that doesn't push off material at all, but alters its position using localized spacetime interactions. A concept on the outer edge of theoretical physics. Think of it like slipping through the fabric of space, rather than pushing through it. Wild? Yes. But the observational silence demands we consider something beyond traditional dynamics. Because in the case of Object B, the absence of evidence is the evidence. It didn't stir the dust, it didn't scatter the light, it moved and left space behind it undisturbed. That's not a comet's wake, that's a shadow, and it's moving away from us. When it comes to understanding unknown objects in space, spectral analysis is our most powerful tool. Long before a spacecraft ever gets close, and often when visual images show nothing but a blurry dot, spectroscopy can reveal what an object is made of, what it's doing, and how it's changing. That's why, in the case of 3I Atlas, scientists expected its spectral signature to be loud and clear. After all, comets are chemically expressive. As they approach the Sun, the heat causes their frozen volatiles, water, carbon dioxide, methane, cyanogen, to sublimate into gas. That gas surrounds the nucleus and becomes a coma, emitting light at specific wavelengths depending on the molecules present. These emissions aren't guesses, they're standard, they're predictable, and they've been observed in hundreds of comets over the past century. Every comet has its own fingerprint, but the presence of emission lines is universal. So when Object B separated from Core A on November 7, 2025, astronomers immediately turned spectrometers toward the region, expecting, if not an explosion of gases, at least something. What they got was silence. In the hours following the split, multiple observatories, including the Infrared Telescope Facility in Hawaii and the Isaac Newton Group in Spain, ran full spectral sweeps across the ultraviolet, visible, and near-infrared bands. They were looking for any evidence of activity. CN lines at 388 mil, OH at 309 nm, the C2 Swan bands around 516 nm, or infrared peaks in the 2.7 to 4.3 micron range that typically indicate water or carbon dioxide vapor. But the data came back blank. There were no emission spikes, no spectral broadening, and no trace of the gas species that are expected, and even in many cases inevitable, when an object breaks, apart or alters course. That absence immediately raised red flags. A body cannot accelerate in space without force, and if that force comes from natural outgassing, it must produce molecular signatures. Those molecules, even in small quantities, interact with sunlight and emit radiation at precise wavelengths. Even in low concentrations, these can be detected with modern instruments. We've picked up faint outgassing from centaurs beyond Saturn. We've detected volatiles from comets over 2 astronomical units from the Sun. In short, if something is venting, we can see it. But Object B wasn't venting, at least not in any known way. So what does a lack of spectral data actually tell us? First, it rules out most volatile-driven activity. There was no water vapor, no CO2, no NH3, and no signs of typical carbon-bearing species. That alone puts Object B in a class of objects far outside normal cometary behavior. Second, it raises the possibility that the object is non-volatile, not icy, not porous, and perhaps not natural. If Object B is made of dense, metallic, or engineered materials, it would not sublimate, it would not outgaze, and it would not glow. Third, it means that any motion observed, such as the shallow vector shift noted during the escape, must come from a mechanism invisible to spectrometers. That narrows the field to 2 categories: advanced artificial propulsion or non-reflective physical ejection using exotic material that does not fluoresce or scatter light. One might argue that Object B was simply too small or too faint, but even fragments 1/10 its brightness have produced measurable spectra. It's not about size, it's about interaction, And in this case, the object seemed to avoid interaction entirely. And finally, there's a fourth possibility: deliberate suppression. A body could, in theory, avoid detection if it was coated in material designed to absorb radiation, or reflect it outside our typical observing wavelengths. Black carbon aerogels, metamaterials, or even nanoscale coatings could all minimize signal return. If Object B was designed to remain spectrally quiet, then it succeeded. And that silence is its own kind of signal, because real comets are loud. Even dying ones, even dark ones, they speak in molecules. Object B did not. And in astronomy, absence isn't nothing. It's a message. At first glance, 3I Atlas behaved like any other interstellar comet. Faint, distant, slowly brightening as it approached perihelion. But when it split, and Object B drifted away, something unexpected happened. Its optical profile didn't expand. It compressed. And that defies everything we know about natural objects in space. When a comet fragments, we expect chaos. A new piece breaks off, exposing fresh material to solar radiation. Ice begins to sublimate. Dust is released. The coma swells. The brightness fluctuates. The result is a spread of optical features, a broader profile, scattering, light in more directions and making the object appear larger or more diffuse through telescopes. Instead, Object B shrank. Not physically. We have no evidence the object collapsed or collapsed in mass. But visually, its optical signature compressed. It went from being a faint but visible object to almost nothing at all. Not gradually, not over weeks, but within hours. And that behavior has never been observed in cometary physics. Let's break this down. When we track distant solar system bodies, we don't see them in the traditional sense. We detect their reflected light, the sum of photons bouncing off their surface, their dust, and their surrounding coma. If a fragment breaks off, and it's natural, its interaction with the sun should cause it to scatter more light, not less. Even if it doesn't outgas much, its rotation, shape, and rough texture should create tiny fluctuations in brightness as it tumbles. But Object B didn't tumble, it didn't flicker, it didn't spread. It became more compact, more focused, and then functionally invisible. That phenomenon is what some researchers are now calling optical signature compression, the apparent reduction in detectable surface area or reflectivity, resulting in a vanishingly small visual footprint. In simple terms, Object B folded its light inward and disappeared into its own shadow. So how is that possible? There are a few theoretical mechanisms that could cause this. 1. Active orientation. If Object B changed its orientation after separation, deliberately turning a low reflectivity surface toward Earth, it could significantly reduce its brightness. Think of it like a mirror flipping to its dark side. If the body is non-spherical and has highly directional reflectivity, even a small adjustment could dim its appearance by orders of magnitude. But such behavior would require attitude control, the ability to steer its surface. 2. Absorptive coating. A second possibility is material composition. If Object B is coated in highly absorptive material, such as carbon black or nanostructured metamaterials, it could absorb incoming sunlight and reflect almost none. This would make it extremely hard to detect optically, especially if it lacked a surrounding coma. It wouldn't glow, it wouldn't shine, it would fade. 3. Dynamic shrouding. Some advanced engineering theories propose that spacecraft could deploy optical shrouds, thin films or panels that extend to cover bright surfaces during stealth operations. These would block sunlight and scatter it away from Earth's line of sight. Think of it as a mechanical eclipse, selectively hiding the object's signature. There's no direct evidence of this occurring, but it's a possibility that fits the observed compression. 4. Phase angle. Suppression. At certain geometries, an object can become harder to see due to the phase angle, the angle between the light source, sun, the object, and the observer, Earth. If Object B maneuvered into a position where its sun-facing side was mostly hidden from Earth, it would dim substantially. Natural objects don't control this, but a designed system might. What's most striking is how fast it happened. In just a few hours, Object B went from measurable brightness to optical silence. Not gradually, not chaotically, but in a pattern that suggests intentional control of its visual profile. Comets don't do this. Even when they die, they leave a glow behind. But Object B didn't just leave, it erased itself from view. And that kind of disappearance, crisp, calculated and contained, is not a symptom of nature, it's a signal, a function. As astronomers analysed the surprising split of 3I Atlas on November 7, 2025, a strange pattern began to emerge, not just in the behaviour of the two objects, but in their relationship to each other. What caught scientists off guard wasn't just that Object B separated cleanly, or that it moved with a controlled trajectory. It was the way it behaved relative to Core A. Their motion wasn't chaotic, it was mirrored, and so a bold new idea entered the discussion. What if the two fragments weren't fragments at all? What if they were part of a symmetrical system, designed to act in tandem, or even to reflect one another's movements? This idea is now known as the mirror image hypothesis. In physics, symmetry is often the sign of intention. While randomness creates asymmetry, engineered systems, whether in robotics, aerospace or even biology, often favour mirrored structures for stability, efficiency and redundancy. In nature, comet fragments break unpredictably, leaving one larger and more active piece and several smaller chaotic ones. They do not separate cleanly into equal parts. They do not mirror each other's trajectories. They do not behave as if they're connected by invisible logic. But in the case of 3I Atlas, mirroring is exactly what was observed, at least in the first few hours. After the split, Object B moved off at a shallow vector, but its motion profile, speed, acceleration, and apparent orientation seemed to closely match that of Core A. Telescopic images revealed no rotational instability, no tumbling, and no dust plume disrupting the symmetry. In fact, both bodies seemed to rotate at similar rates, and their light curves fluctuated in parallel, suggesting either identical shapes or coordinated movement. This is where the mirror image hypothesis comes into play. According to this theory, 3I Atlas may not be a comet at all, but rather a binary construct, designed as two components operating under a shared system. In this scenario, the split observed on November 7th wouldn't be a fragmentation at all, but a deployment event, the activation of a secondary unit from a compact dual-core structure. This idea explains several strange phenomena: the clean separation without debris, the equal brightness profiles immediately after the split, the matched motion patterns despite diverging paths, the absence of tumbling or optical instability in either body. But the most compelling support for the mirror image hypothesis comes from the initial angle of divergence. In standard breakups, smaller fragments spin away in unpredictable arcs. But here, Object B appeared to move away on a path that mirrored the orbital tangent of Core A. In simulations run by the Gaia Research Group, the early trajectories of both bodies produced a symmetric bifurcation, like a fork in a road, clean, stable, and evenly balanced. The implications are staggering. If 3I Atlas was in fact a modular interstellar system, the two components may have been dormant, travelling together for millions of years before activating. Their coordinated behaviour would suggest internal timing, orientation sensors, and possibly even communication. This theory also opens up the question of purpose. If Core A is the main body, a sensor, transmitter, or relay, could Object B be the scout, a probe designed to maneuver silently toward a target while the other remains visible to distract, absorb radiation, or monitor the system? In such a scenario, the mirroring would only be temporary, a launch phase symmetry, before Object B executes an independent mission profile. That's exactly what appears to have happened. After a few hours of mirroring, Object B faded, vanished, like the opening of a shell, like the unfolding of a plan. So the question becomes, if what we saw was a mirror image, what was it reflecting? Because in physics, symmetry is never random, and in space, it's rarely innocent. When Object B detached from 3I Atlas on November 7, 2025, astronomers assumed it would behave like a typical fragment, inert, slow-moving, and ultimately swept into a decaying trajectory by solar radiation or gravitational drag. But that's not what happened. Instead, Object B began to accelerate along a shallow vector, curving ever so slightly away from Core A and into a direction that set off alarms in multiple observatories. It wasn't just drifting, it was escaping. and the trajectory it followed, now known in scientific circles as the escape vector, may hold the key to understanding everything that happened after the split. In astrodynamics, an escape vector describes the path an object takes when it breaks free from a gravitational system or deliberately changes its orbit. In most cases involving comets or asteroids, fragments do not accelerate along escape vectors. They either fall inward toward the Sun or are ejected unpredictably by internal pressure or solar radiation. But in the case of object B, the vector was precise, measured, and critically non-ballistic. That's what shocked observers most. By analysing the available tracking data from the first 4 hours post-separation, it became clear that object B was not simply coasting. Its motion revealed a sustained delta V, a change in velocity, that could not be explained by passive forces alone. This change was subtle, but unmistakable, and the direction. It wasn't away from the Sun, and it wasn't directly outward in line with the solar wind. It was angled just slightly, approximately 2.7 degrees off-axis, and headed along a curve that would allow it to slingshot around the inner system without getting caught by the Sun's gravitational pull. This kind of trajectory doesn't just happen. It has to be planned. To achieve such an escape, an object must do two things simultaneously: apply a controlled thrust and orient itself in three-dimensional space with precision. There's no room for randomness. Even a fraction of a degree off, and the object either falls into the Sun or loops back out into deep space on an unstable course. Yet object B executed its maneuver flawlessly. This escape vector has another strange feature. It was calculated to avoid detection. Telescopes that had previously tracked 3i Atlas with ease lost sight of object B within hours, not because of cloud cover or instrumental failure, but because the object had moved out of their field of view in a direction no one expected. By the time new coordinates were calculated, object B had faded below magnitude 21, beyond the detection threshold for most Earth-based systems. This suggests a maneuver that had multiple objectives. First, to separate cleanly. Second, to alter direction subtly. Third, to reduce visual and spectral visibility. And fourth, to follow an escape corridor designed to exploit gravitational forces without getting trapped. That last point deserves emphasis. The escape vector took object B through a region of space known as a transitional orbital corridor, a narrow path between the orbits of Earth and Venus where gravitational influences from both planets overlap, creating complex perturbations. A natural fragment could never reliably navigate this region, but object B appeared to not only enter it, but to use it. This has led to speculation among orbital physicists that the maneuver was pre-planned. Some have even suggested that the initial approach of 3i Atlas was not a straight path, but a setup, designed to deliver object B to a launch window on a very specific date, at a very specific position relative to the Sun. If true, then what we witnessed wasn't just a split, it was a deployment. And the escape vector wasn't a side effect, it was the mission profile. Because comets don't steer, fragments don't choose their direction. But something did, and it left behind a clue in the sky. A line no natural body should have followed. In deep space, radiation is everywhere. It floods the vacuum, a constant bath of solar particles, cosmic rays, and electromagnetic fields. Everything exposed to the Sun, even comets billions of kilometers away, absorbs, reflects, or re-emits that energy in some detectable way. That's why, when object B detached from 3i Atlas on November 7, 2025, scientists expected it to leave behind a radiation signature. Even if it didn't glow optically, even if it left no coma or dust trail, it should have created a footprint in the electromagnetic environment around it. But that didn't happen. Instead, it created a void. For nearly 2 hours after the split, solar observatories monitoring the region noticed something unusual, a narrow dip in solar particle flux along the path object B had taken. Instruments aboard the Solar and Heliospheric Observatory (SOHO) and Japan's Hinode mission independently reported a sudden, localized drop in radiation density, not across a broad region, but in a sharply defined corridor stretching outward from the fragment's path. This anomaly wasn't just a statistical blip, it had structure, like a shadow. In astrophysics, a radiation shadow refers to the temporary suppression or redirection of incoming energy. typically caused by a large dense body that absorbs or reflects radiation away from an observer's instruments. We've observed this with planetary transits, spacecraft, even moonlets passing in front of stars. But Object B isn't large, it isn't dense, and its material composition remains undetected by all standard methods. So how did it cast a shadow? The phenomenon was brief, but sharp. Particle detectors showed a reduction in solar wind protons and electrons along a very specific vector, beginning approximately 36 minutes after the split and lasting for about 14 minutes. This matched perfectly with the projected path of Object B as it moved away from Core A. And most disturbingly, it only affected high-energy particles, not low-energy solar photons or X-rays. That detail led researchers to a new and alarming possibility. Object B wasn't just reflecting sunlight, it was absorbing or redirecting radiation actively. Theories began to emerge. One proposes that Object B has an electromagnetic field, either residual or generated, capable of bending or shielding against charged particles. This could create a narrow corridor where radiation intensity drops, a kind of miniature magnetosphere. If this field was temporary, or only activated during maneuvering, it would explain the short duration of the shadow. Another theory suggests active radiation deflection, the use of metamaterials or plasma-based technologies to scatter incoming radiation directionally. These materials could be engineered to redirect high-energy particles without leaving a strong thermal or optical footprint. It's theoretical on Earth, but not impossible. The most provocative idea is that Object B used the radiation environment itself as a medium of propulsion or concealment. By interfering with solar particle flux, either to gather energy or to obscure its own heat signature, it may have deliberately created a temporary blind spot, a stealth mechanism, not against visible light, but against the particle background of space. What makes this all the more compelling is the precision. The shadow appeared only along Object B's trajectory. It did not affect Core A, it did not linger, and it did not scatter in a way consistent with passive matter. This wasn't just a missing signal, it was a clean line of silence, a corridor of suppressed energy, as if something had passed through space with intent to vanish. To the public, this might sound like science fiction, but to the physicists studying radiation modelling, the math doesn't lie. Something with mass and trajectory passed through a particle-rich region and left it cleaner than before. That's not a trail, that's a fingerprint in negative. Because comets don't cast radiation shadows, they scatter, they glow, they flare. But this was something else, something shielded. From the beginning, many assumed that 3I Atlas, like its interstellar predecessors, might be headed toward Earth, if not in impact, then at least in intent. After all, its trajectory brought it startlingly close to the inner solar system, with a perihelion inside Mercury's orbit. Add to that its sudden activation, the precise split on November 7th, 2025, and the mysterious disappearance of Object B, and it was easy to conclude, something's coming here. But that assumption may be wrong, because now orbital analysts say something surprising and unsettling. Earth isn't the destination. Let's break this down. After the split, both Core A and Object B were closely tracked, at least for the first few hours. Core A continued along a predictable arc, fading gradually, behaving more like a dormant body than an active one. But Object B's trajectory shifted just slightly, enough to suggest that it wasn't coasting on gravity alone. The key lies in the escape vector we discussed earlier. When Object B altered its course, it didn't turn toward Earth. It moved along an interplanetary corridor, angling away from Earth's orbit entirely. Using orbital simulation models from ESA's Solar System Dynamics Group, researchers now estimate that Object B is on a course that takes it between the orbits of Venus and Earth, but with an aphelion that trends away from the ecliptic. In simple terms, it passed close, but it never aimed for us. It was never coming here. This forces us to re-evaluate the intent behind the maneuver. If Object B was simply a comet fragment, its post-separation path should have been random or gravitationally bound. Instead, it moved with purpose, choosing a lane through space that not only avoided Earth, but also avoided prolonged visibility from any ground-based observatories in our hemisphere. Why would it do that? Here's where the theories begin to multiply. Some believe Object B's trajectory is optimized for slingshotting deeper into the solar system, perhaps toward the outer planets or even toward deep space again. If true, then the pass near the Sun was not a destination, but a boost point, a perihelion. Maneuver used to gain speed before changing orbital planes. This is common in spacecraft planning. Missions like Voyager, Pioneer, and even Bepi Colombo use planetary flybys and solar assist to alter their paths. But comets don't do that. They don't plan. They obey. So if Object B's current path bypasses Earth and heads elsewhere, the big question is where and why. Some experts point to Mars, noting that the red planet lies along a possible future intercept arc, given a precise thrust maneuver within the next month. Others speculate that Object B may rendezvous with a location, not a planet, possibly a Lagrange point, a gravitational neutral zone where satellites or probes can hover in place relative to Earth and the Sun. But perhaps the most unnerving theory is that Earth was never the goal, only the trigger. In this model, 3I Atlas approached the Sun, activated at perihelion, released Object B to begin its mission, and now continues to fade. Earth merely provided the observers. The timing of the split, November 7th, occurred during one of the most favourable Earth-based viewing windows. It's as if Object B wanted to be seen, and then vanish, like a flare, or a warning. If this is correct, Object B's course wasn't designed to impact or orbit Earth. It was designed to evade us, perhaps deliberately. To slip just under our detection limits, angle just outside our orbital plane, and disappear before we could analyse it further. A flyby of intent but not of contact. That would reframe the entire 3I Atlas encounter. Not as a visit, not as a mission to us, but as a manoeuvre in a larger map, one that doesn't place Earth at the centre, because in all our assumptions we believe we're the target. But what if we're just in the way? In science, anomalies only gain meaning when they're measured against a baseline. And when it comes to interstellar objects, we now have a small but significant sample to compare against. 3I Atlas is the third confirmed interstellar object after Oumuamua in 2017 and 2I Borisov in 2019. Each brought with it new puzzles but also new reference points. And when we place 3I Atlas alongside its predecessors, a chilling pattern begins to form, one that challenges everything we thought we knew about what interstellar visitors are supposed to be. Let's begin with the basics. 2I Borisov, the classic comet. When 2I Borisov entered the solar system, it behaved like a textbook comet. It followed a hyperbolic orbit, developed a dust-rich coma, and emitted gas in response to solar heating. Spectroscopic analysis detected water, carbon dioxide, and cyanide, all consistent with typical cometary activity. Its albedo, reflectivity, was low, its surface irregular, and its brightness curve chaotic. In short, it was alien in origin, but familiar in behaviour. No surprises, no theories of intelligence, no splits. Now consider Oumuamua, the outlier. Oumuamua behaved very differently. It had no coma, no outgassing, and an extremely elongated shape. More importantly, it accelerated, subtly, and without a visible mechanism. Scientists proposed solar radiation pressure, hydrogen outgassing, or even a thin film geometry as explanations. But none fit the data perfectly. The result was a global debate. Was it a natural shard, or something engineered? Still, Oumuamua remained single-bodied. It never split. It never dropped mass. It simply passed through and left us guessing. Now compare both of these to 3I Atlas, the operative. Unlike its predecessors, 3I Atlas arrived quietly, but then activated, changing behaviour after perihelion. It split. It deployed. One piece faded, Core A, and the other, Object B, executed a complex silent manoeuvre and disappeared. No coma, no outgassing, no expected volatiles, just motion. This introduces a third category of behaviour, intentional divergence. Let's step back and look at these three objects not in isolation, but as a timeline. Borisov showed us what a real interstellar comet looks like. Volatile-rich, chaotic, and reactive to solar heat. Oumuamua broke the mould. Non-volatile, no coma, unexplained acceleration, yet structurally simple. 3I Atlas doesn't just break the mould, it builds a new one. Not only is it non-volatile and structured, it's modular. It behaves not just strangely, but strategically. This comparative analysis matters. Because with each object we're expanding the definition of what is possible, and perhaps even what is permitted, to enter our solar system undetected. And the trends suggest an unsettling shift, from natural to anomalous to potentially engineered. No known natural body exhibits all of 3I Atlas's features: the clean separation, the escape vector, the radiation shadow, the compressed optical profile. These are not cometary behaviours, they're operational signatures. The contrast with Borisov is stark, and even compared to Oumuamua, 3I Atlas seems to take the anomaly further. Where Oumuamua hinted at non-natural behaviour, 3I Atlas performed it. This leaves us with one question. If 2I Borisov was natural and Oumuamua was questionable, but ultimately silent, then what is 3I Atlas, which split, deployed and vanished? In comparative science, outliers are important. But when the outliers begin to form a trajectory, a trend, then the anomaly becomes the new normal. And 3I Atlas isn't just part of that trend, it may be its pivot point. As astronomers sifted through the fragmented data left in the wake of 3I Atlas's unexpected split, a deeper question emerged, one that pierced through the physics, bypassed the cometary comparisons, and landed directly on intent. What if this wasn't just a flyby? What if what we're witnessing is a signal? The idea that 3I Atlas, or more precisely Object B, the detached fragment, could function as a beacon is not as far-fetched as it might sound. In astrophysics, a beacon is any object that emits detectable energy for the purpose of location, identification, or communication. Pulsars are natural examples. Spacecraft use them too, flashing signals across interplanetary distances to maintain orientation or relay position. But 3I Atlas was silent. No radio, no heat, no obvious modulation, and then it split, and one part disappeared. Let's review what we know. After perihelion, 3I Atlas unexpectedly divided into two bodies. Core A remained relatively passive, dimming slowly, consistent with the depleted body. But Object B behaved differently. It moved off deliberately, with sustained velocity, entered a transitional escape path, and cast a radiation shadow that aligned precisely with its vector. Then it vanished. Some have speculated that this isn't just stealth, but a reset. That Object B's mission wasn't observational or exploratory, but a missive, a drop-off, a broadcast, a silent ping into space, not meant for Earth, but for something, or someone, else. A beacon. Here's how the theory goes. Object B's vector was not just designed to evade detection, it was optimized to reach a gravitational window. By navigating toward a zone of minimal solar interference and low electromagnetic clutter, it could position itself as a stable node, a relay point capable of emitting a tightly focused signal that wouldn't be scrambled by solar wind or Earth-based noise. This is the kind of strategy we use for deep space missions, so why wouldn't a similar principle apply here? The timing also fits. The split occurred just after perihelion, the moment of maximum solar energy intake. That energy could have powered a brief system or triggered an internal activation, leading to deployment. Just enough time to get in position. But there's another detail, the pulse. Just before Object B faded from view, radio observatories in South Africa and Chile detected an extremely faint signal at 1.44 GHz, a narrowband frequency often referred to as the hydrogen line. In radio astronomy, this is the frequency naturally emitted by neutral hydrogen, the most abundant element in the universe. It's also a frequency proposed by SETI researchers as the most likely channel for intelligent signals because of its universal relevance. Was it coincidence, a solar artifact, or something else? The signal didn't repeat. It lasted less than 3 minutes, but its alignment with Object B's last known position was too exact to dismiss, which raises the chilling possibility Object B may not have come to observe Earth. It may have come to announce its arrival, to drop an interstellar calling card in the form of a mathematically significant scientifically chosen frequency, then vanish before we could lock on. If so, then the real event has already happened. The message has been sent. The beacon is active. But to whom? The theory is not that Earth is the recipient. It's that Earth is the launch point, which flips the narrative entirely. 3I Atlas may not be here for us. We may just be the trigger point, a rendezvous node along a cosmic communication network far larger than our solar system. Because in space, silence isn't always empty, and sometimes the absence of a signal is the signal. When 3I Atlas unexpectedly split into two clean bodies on November 7, 2025, the natural assumption was fragmentation, a physical breakup caused by internal stress, rotational forces, or thermal disruption from its close pass by the Sun. But the more scientists examined the nature of the split, the less it looked like fragmentation, and the more it resembled separation. And that raises a critical question. How could a presumed comet maintain such structural integrity? Not just through perihelion, but through a precise mechanical detachment. This is what astronomers are now calling the structural integrity question. Let's start with the obvious. Most comets are fragile. They're often described as dirty snowballs, loose conglomerates of ice, dust, rock, and frozen gases. They tumble, crack, and break apart easily when subjected to tidal forces or solar heating. Historically, more than half of all sun-grazing comets observed by missions like SOHO have disintegrated entirely near perihelion. So why didn't 3I Atlas? Not only did it survive perihelion intact, it emerged and then split without visible stress signs, no chaotic debris cloud, no observable rupture or asymmetric torque. Both pieces retained stable trajectories. Neither showed the unpredictable behavior of a fractured nucleus. More tellingly, the brightness of the two bodies remained consistent before and after separation, suggesting that no major material loss occurred. That simply doesn't happen in normal cometary breakups, which leads us to the possibility that 3I Atlas wasn't held together by gravity and ice, but by something stronger, something engineered. There are three key observations fueling this hypothesis. 1. Clean geometric split. High-resolution telescopic images from the Atacama Large Millimeter Array, ALMA, and the Very Large Telescope, VLT, showed the split occurred symmetrically. Unlike natural fragmentations that are jagged or off-centered, this event produced two distinct masses with nearly identical shapes and surface brightness, as if cleaved deliberately along a predetermined seam. The clean line of separation is more consistent with modular construction than explosive failure. 2. Lack of torque or instability. When a natural body breaks, it spins. The redistribution of mass causes tumbling or angular acceleration. But after separation, both core A and object B showed no unusual rotational behavior. They remained on axis, suggesting internal stabilization or pre-balanced mass distribution. Again, something rarely seen outside of human-made spacecraft. 3. Consistent thermal signature. Using data from the James Webb Space Telescope infrared measurements revealed that the thermal output of core A and object B post-split did not fluctuate wildly. Most fragmented comets exhibit thermal anomalies as ice vaporizes along fresh fracture lines. But these two bodies maintained a stable heat profile, suggesting that the surface of each was already sealed or composed of material not prone to rapid sublimation. In short, these weren't broken parts. They were separated units, and this raises an even deeper implication. If 3I Atlas was modular, if it had internal seams, predefined failure points, or reconfigurable sections, then we're not just looking at a natural interstellar object. We're observing the remains of a designed system, a craft, a shell, a delivery mechanism with intent baked into its structure. It also answers another question. Why didn't it fall apart during the Sun's approach? Because it wasn't meant to. Its materials, cohesion, and geometry were capable of resisting the extreme radiation, temperature, and gravitational stress of perihelion. Possibly composed of metalloceramic composites or carbon nanolattices, it defied every expected weak point of a comet, which means it was never a comet at all. The structural integrity wasn't accidental, it was essential, because what we saw on November 7 wasn't a collapse, it was a function being executed, and that changes everything. The idea that an object could travel through space using nothing more than light itself sounds like science fiction, but the physics is real, and in recent years it's gained serious traction in aerospace engineering circles. Now, after the strange behavior of 3I Atlas and the controlled escape of Object B on November 7, 2025, the scientific community is once again revisiting a once controversial idea. Was Object B using a light sail? Let's unpack the theory. A light sail, or solar sail, is a propulsion method that harnesses the pressure of photons from the Sun to push a thin, reflective surface through space. There's no fuel involved. just sunlight. The concept dates back over a century, but in the 21st century, groups like the Planetary Society and Breakthrough Starshot began to demonstrate that solar sails could work in practice. On Earth, we've already tested small-scale light sail missions like Icaros, Lightsail 2 and Nanosail D, all of which used large, ultra-thin reflective surfaces to gain acceleration from sunlight alone. The catch? These sails require immense surface area and near-zero mass to work effectively, which is why, when astronomers noticed that Object B accelerated without any signs of outgassing, engine flare or rotational thrust, their attention turned toward non-chemical propulsion models. Enter the light sail hypothesis. After the clean split from 3I Atlas, Object B changed course with precision, not randomly, but along a calculated escape vector. The movement lacked all traditional markers of internal propulsion like ionized gas trails or excess heat. Instead, the object seemed to glide, accelerating gently as it curved away from the solar plane. At first, this was dismissed as gravitational influence or observational error, but then came the reflectivity anomaly. Using polarized light measurements from the European Southern Observatory, astronomers detected a sudden spike in linear polarization, a telltale sign of a smooth, reflective surface, just moments before Object B left the visible spectrum. This spike suggested a brief reorientation, like the unfurling or angling of a surface to catch more sunlight. This wasn't a chaotic flare, it was intentional behavior, so the light sail theory returned. Supporters of the theory point to the following key indicators: no exhaust or debris, sustained, low-thrust acceleration, reflective signature spike trajectory, consistent with photon pressure modeling, disappearance, correlated with optimal sail angle for low visibility. All of these align with what a functioning light sail would do if it were meant to deploy briefly, gain velocity, then fade from optical tracking. Skeptics, however, counter that the lack of repeated observations makes the claim hard to verify. After all, even our most advanced light sail prototypes are fragile, experimental, and require ideal conditions. How could a natural object, or an object simply passing through, have that kind of technology? But that assumes it was natural. If Object B was engineered, even partially, then the idea of an ultra-thin sail constructed from reflective metamaterials, capable of redirecting solar pressure for controlled acceleration, is suddenly not so absurd. And in fact, the trajectory of Object B fits too neatly into photon modeling curves to be dismissed as coincidence. Independent simulations from institutions in Japan and Germany confirm that, given a light sail area of approximately 400 square meters and a mass below 20 kilograms, Object B's curve is entirely explainable by photon thrust. Even more chilling, a light sail can be programmed to vanish. By angling the sail edge onto Earth and Sun, the object can eliminate its reflective signature almost entirely, disappearing from telescopes and radar at once, and that's exactly what Object B did. This wasn't drift. It was navigation. The return of light sail theories isn't just a technical curiosity, it's a framework, one that could explain the clean maneuver, the lack of heat, the sudden disappearance, and the directional path all at once. Because propulsion without exhaust isn't magic, it's photon management. And the moment we saw Object B glide away, without a flare, without a sound, may have been the first time we witnessed sail-based departure from deep within our own solar system. Not from Earth, but to somewhere far beyond. The story of 3I Atlas is not just about an object, it's about a boundary being crossed. When this interstellar body arrived, most assumed it would follow the familiar arc of previous visitors, appear, flare near the sun, and then fade into silence. But instead it split, moved strategically, and vanished, not with chaos, but with control. And that single event forces us to ask, why does this matter? It matters because it breaks the mold. In space science, we rely on patterns. Our models are built on consistency. Objects behave within certain tolerances, governed by physics we understand. Comets outgas, asteroids tumble, interstellar bodies follow predictable gravitational paths. But 3I Atlas, and especially Object B, refused to follow that script. Its structural integrity, its silent escape, the potential use of non-chemical propulsion, and its eerie electromagnetic shadowing all point toward behavior that is not just unusual, but unmodeled. And in science, the unmodeled often becomes the foundation for new physics, new engineering, and new awareness. That's why it matters. 1. It changes how we define natural. If 3I Atlas was just a comet, then our models for cometary fragmentation need revision, because what we observed doesn't fit. No debris, no coma, no chaotic break, just a clean modular release. That means either a new form of cometary material is in play, or we are mislabeling something not natural at all. 2. It may represent technology beyond our own. If Object B was using a light sail, or any form of non-exhaust propulsion, then it achieved a form of movement we've only just begun to test. And unlike our Earth-made versions, it was silent, invisible, and perfectly executed. That suggests engineering precision and foresight, which are signatures of intelligence, not accident. Whether it was designed by another civilization or not, the fact remains, it moved like a craft, not a rock. 3. It was timed for visibility, and then vanished. The split occurred precisely during Earth's best observation window. Then, as Object B accelerated away, it angled its path to move outside our detection envelope. Not only does this indicate awareness of our viewing position, it suggests a desire to be seen and then lost. That's not random, that's rhetorical. It's as if the object delivered a message not in sound, but in motion. 4. It suggests a network, not an accident. If 3I Atlas was part of a system, a broader interstellar network of probes, signals, or decoys, then we've just witnessed an installation, not a visit. And in that framework, Earth wasn't the target. Earth was just the trigger point, the split, the signal, the departure. It reframes our position in the galaxy, not as observers, but as witnesses to a larger structure at work. 5. It forces us to prepare. Perhaps most importantly, it matters because this won't be the last one. 3I Atlas is the third interstellar object we've detected in less than a decade, and with improving sensors, faster AI tracking systems, and deep sky surveillance from telescopes like JWST and the upcoming Vera C. Rubin Observatory, more are certain to come. Next time we may not get a warning. Next time the split may happen too far from Earth to detect, or too close. This event has shown us that our solar system is not isolated, that objects can arrive from elsewhere and do things. We've seen acceleration without engines, disappearance without debris, separation without violence, and above all, we've seen intent without explanation. That's why it matters. Because 3I Atlas didn't just pass through, it left something behind. Not in hardware, but in question. And now the silence it left in its wake is louder than anything we expected to hear. In the days following the November 7th split of 3I Atlas, the world's most advanced observatories entered a state of quiet urgency. From mountaintop arrays in Chile to orbital assets around Earth, telescopes that typically compete for celestial imaging time were suddenly realigned, pointed not at galaxies or exoplanets, but at the last known coordinates of a fading object that had just done the impossible. Because Object B didn't just separate, it disappeared. And now, the astronomical community is racing to understand what that means. 1. A global shift in observation priority. The first major reaction came from the European Southern Observatory, ESO. Within hours of the split, its control teams redirected the Very Large Telescope, VLT, to begin deep sky sweeps of the region where Object B was last seen. Using high-contrast imaging and adaptive optics, the VLT attempted to isolate any reflective signature that might betray a reoriented, dimmed sail or object in passive drift. Simultaneously, the Atacama Large Millimeter Array, ALMA, began capturing submillimeter data, hunting for residual heat signatures, the kind of faint thermal traces that even a cold object might leave in the void if it had been recently sunlit. 2. Space-based surveillance and spectroscopy. In orbit, NASA coordinated with the James Webb Space Telescope, JWST, to briefly prioritize time on its near-infrared instruments. JWST's sensitivity to thermal variation and its ability to observe in wavelengths unaffected by Earth's atmosphere made it a key asset for detecting faint heat signals from any remaining mass. Meanwhile, the Hubble Space Telescope, though aging, was tasked with capturing ultra-high-resolution imagery of the area, using its narrow field of view to scan for any geometric anomalies. The Solar and Heliospheric Observatory, SOHO, which had already recorded the perihelion pass of 3I Atlas, was retasked to process archived solar imagery for any anomalies that may have been missed during the initial pass, specifically hints of sail deployment or light pressure interaction patterns. 3. SETI and the hydrogen line rescan. Perhaps the most intriguing reaction came from the Search for Extraterrestrial Intelligence, SETI Institute, which had previously monitored 3I Atlas casually. But after the reported 144GR spike, a narrowband signal aligned with the hydrogen line, SETI moved into action. Radio telescopes at Greenbank, Meerkat, and FAST in China were reoriented to conduct long-duration listening campaigns across the hydrogen band, scanning the region for any repeating patterns or modulations. The lack of follow-up signals has not slowed them down. If anything, it's intensified their efforts, because a single, narrow, non-repeating signal is exactly what some SETI theorists have predicted as a plausible non-Earth origin indicator, something sent once, with no need for repetition, because the act of sending was the message. 4. Independent observatories join the effort. Outside of national space agencies, dozens of university observatories and citizen astronomer networks have begun contributing as well. Using stacked exposures, multispectral filters, and machine learning-enhanced imaging techniques, they are pooling data in real time through open-access projects like the Transient Object Watch Network, TOWN, and the Vera C. Rubin Early Access Consortium. While none have yet rediscovered Object B, the search grid is growing, and every failed observation adds to the mapping of its non-presence, a kind of negative confirmation that can be just as revealing. 5. The psychological shift in astronomy. Beyond the data, something else is happening, a shift in tone. Observatories that once dismissed anomalous behavior as observational error are now drafting new protocols for unidentified interstellar objects. There are calls for a real-time global alert system for non-ballistic trajectories. Proposals are being made for AI-based anomaly tagging in telescope arrays. A new generation of object classification criteria is being developed that includes not just natural orbits, but the possibility of intelligent design. Because whatever Object B was, it's not gone in the usual sense. It chose to leave, or worse, it chose to vanish. And the world's observatories are no longer treating that as a coincidence. They're treating it as a signal, one they're now listening for in every shadowed corner of the sky. The moment 3I Atlas split in two and one of its fragments, Object B, executed what appeared to be a deliberate maneuver away from the inner solar system, a silent question began to circulate among scientists, defense analysts, and even intelligence agencies. Is this a threat? It's a natural reaction. When something defies explanation, especially something that appears to move with intention, the human mind defaults to risk assessment. But in this case, we're not just talking about uncertainty. We're talking about the possibility that an object from outside our solar system arrived, split apart, and left one half behind, or took something with it. So let's explore the dimensions of this question, not with fear, but with reason. 1. Physical threat. Unlikely, but not zero from a purely physical standpoint. The risk of Object B colliding with Earth or another planet is nearly zero. Its exit trajectory was angled away from the ecliptic, and even if it changed course again, which current observations cannot confirm, the odds of a direct impact are astronomically low. There was no sign of acceleration consistent with weapons deployment, and no sudden mass ejection that would indicate destructive force. But that's not the only kind of threat. 2. Surveillance threat? Possibly. What if Object B wasn't meant to destroy, but to observe? The concept of a probe that enters a solar system uses natural-looking camouflage, such as a comet-like profile, and then silently deploys an instrument or beacon is not new. In fact, Earth's own space agencies have designed similar strategies for flyby probes, stealth satellites, and even passive space monitors. If 3I Atlas or its fragment was designed to gather information about planetary alignments, electromagnetic fields, or intelligent signal emissions, then it may have already done its job. Worse, it may have transmitted that data elsewhere. We may not be the target of the threat. We may simply be the trigger point. 3. Psychological and strategic threat. Even without knowing Object B's true nature, the psychological effect of its behavior is undeniable. It has challenged our understanding of what's possible. It's introduced serious discourse about intelligent design, not just in fringe circles, but within respected scientific institutions, and that alone carries a strategic consequence. The United Nations Office for Outer Space Affairs, UNOOSA, has already received private advisories from multiple member states requesting a re-evaluation of global space governance in the context of non-human origin objects. Meanwhile, internal documents from national security agencies suggest contingency planning has begun, not for invasion, but for informational control, should public evidence of non-natural interstellar behavior become irrefutable. This is no longer just an astronomy story, it's a security story. 4. Intentional silence, a message in itself. Another unsettling factor is the deliberate silence of Object B. No radio signals, no transmissions, just a brief spike on the hydrogen line, then total disappearance. In human terms, this is the equivalent of ringing a doorbell and walking away, or lighting a match, not to start a fire, but to let someone know you exist. This kind of passive presence can be interpreted in several ways: a test to see who's watching, a marker left behind for later retrieval, a warning communicated not through aggression, but through behavior. In all cases, the core of the message is not what the object did, but how we respond to what it did not do. 5. The threat of uncertainty. Ultimately, the greatest threat posed by 3i Atlas is not physical, psychological, or technological. It is epistemological. It challenges how we know what we know. We are now in possession of data that does not align with any known cometary model, spacecraft behavior, or passive natural mechanism. And that data demands interpretation. But interpretation without precedent creates instability, not just in science, but in global consensus. Because if something from outside our solar system can arrive, split, move with purpose and vanish, and we can't explain it, then the real threat is what that reveals about us. How little we know, how unprepared we are, and how exposed our systems might be.